Welcome to cybersecurity under pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
I don't know about your week, but after the sheer volume of architecture reviews I've been drowning in, I am very ready to just sit back, decompress, and share a virtual drink with you, our listener. We somehow dragged ourselves across the finish line of another week.
Barely. I mean, we survived, sure. But looking at the stack of research sitting on the desk today, I might need to make that drink a double. We are watching the industrial networking landscape undergo a complete existential crisis in real time.
This one has it all: a real incident, a lesson nobody wants to hear, and a detail that will make you check your own systems. We're doing a deep dive into the massive tectonic shift happening across manufacturing and critical infrastructure. Basically, the great migration from wired ICS to 5G.
Because everyone is chasing the mobility, the data density, the sub-millisecond speed. But they are ripping up the moat to build a highway, and they don't quite realize what they're letting into the castle.
Exactly. To unpack this, we are looking at some seriously heavy-hitting data. We've got packet-level analysis from the SYCS testbed, that's the simulated wireless ICS environment, alongside this cutting-edge research out of the University of Padova on AI threat detection at the radio layer.
Right, and plus we're tearing into the IEC 62443 standard and looking at how giants like Siemens and Palo Alto Networks are architecting real-world rollouts. Because we need to look at the promise, the terrifying new vulnerabilities, and the actual blueprints for surviving this wireless frontier.
We really need to start with the foundational motivation, I think. Because if you sit down with a veteran OT engineer and suggest pulling out their rock-solid, deterministic copper Ethernet cables to replace them with probabilistic radio waves,
They will laugh you out of the plant.
or literally throw you off the catwalk. They've spent decades building systems where availability and real-time operation are the only metrics that actually matter.
Right. Confidentiality, integrity, those are nice to haves in traditional ICS, but if a safety interlock triggers, that Profinet packet needs to arrive in under a millisecond every single time. A copper wire delivers that. It's static, it's rigid.
Which is precisely the bottleneck for Industry 4.0. Right? The physical wire is the ultimate constraint on flexibility. You can't have a fleet of AMRs dragging Cat6 cables across the logistics floor like a pack of robotic dogs on tangled leashes. It physically doesn't scale.
No, not at all. The industry demands autonomous mobility, digital twins ingesting high-frequency telemetry, massive uplink capacity, and we all know Wi-Fi simply cannot handle deterministic sub-millisecond control loops.
Oh, absolutely not. Wi-Fi MAC layer scheduling is essentially a polite conversation. CSMAGI is just devices yelling over each other and backing off when they collide.
Yeah, and it operates in unlicensed spectrum, which means a forklift's reversing beacon or a microwave in the break room can completely destroy your jitter budget. That is why 3GPP release 16 and 17 position 5G as the true successor. We aren't just talking about broader bandwidth.
We're talking URLLC, right? Ultra-reliable, low-latency communication.
Exactly. The entire frame structure of the 5G new radio was redesigned with many slots and preemption mechanisms to guarantee that a critical safety payload can bump routine traffic out of the way on the air interface.
And this isn't just white paper theory anymore for you listening. The sources detail actual live pilot deployments. Look at Siemens and their Nuremberg test center. They bypassed the commercial carriers entirely and deployed a private 5G standalone network and SA architecture using the 3.7 to 3.8 gigahertz industrial band.
The standalone distinction is critical there. By deploying a 5G core on premises, they ensure the user plane function, the UPF, routes the industrial traffic locally.
It never leaves the building.
Right. It never backhauls to a telecom operator's regional data center. Because if your Profinet traffic has to bounce to a telecom hub and back, you've already blown past your 1 millisecond latency budget just in fiber transit time alone.
Then look at Gestamp in Barcelona. They partnered with Telefonica to hook up robotic welding cells to 5G. The robots stream high-resolution point clouds and torque feedback to a digital twin in real time.
That's a massive amount of data.
It is. The twin instantly runs finite element analysis and dynamically adjusts the welding parameters for the very next car chassis on the line. Legacy systems would buckle under the payload.
The sheer volume of uplink throughput required for uncompressed sensor fusion like that is staggering.
And we also have AT&T and Samsung deploying millimeter wave 5G in Texas for mixed reality training. They're using augmented reality headsets on the factory floor, streaming live video overlays and high-def feeds back to a remote expert. Completely untethered, pushing multi-gigabit throughput without dropping a single frame of render.
The operational agility is undeniably revolutionary. It allows manufacturers to reconfigure an entire assembly line over a weekend without pulling new conduit.
But, and this is the massive looming but hanging over this whole transition for you and your teams, cutting those physical Ethernet cables to the machinery feels exactly like cutting an umbilical cord.
It's the perfect way to frame it.
Think about it. The umbilical cord is restrictive, yes, but it provides a closed, protected, highly predictable environment. You cut it, and suddenly your autonomous robots can roam anywhere, your digital twins are breathing live data, and you are totally liberated, but you are now completely exposed to the elements.
Yeah, the physical trust boundary of that closed copper loop is just gone.
The architectural shift fundamentally alters the threat model.
It does. By moving to non-public networks, NPN's companies gain data sovereignty, keeping their proprietary manufacturing telemetry off commercial networks. But they simultaneously move the OT risk to a domain that industrial security teams have absolutely no experience defending.
The radio layer.
The radio frequency layer. For 30 years, securing a plant meant physical air gaps, port security, MSC filtering, and preventing rogue USD drives. Now, the attack surface is the actual atmosphere inside the facility.
The air itself, the physical perimeter of the building no longer defines the network boundary. RF bleeds through drywall, it bounces off metal silos.
Which brings us to the core issue. Since the risk has shifted to a probabilistic medium like radio, we have to examine what happens when that medium is compromised. What does the cyber attack in the air actually do to the kinetic physical machinery?
This is where the SEXWE ICS testbed research provides some terrifying clarity. Simulated wireless ICS. The researchers built a highly accurate virtual environment of a 5G-enabled industrial loop and ran attacks against it under two conditions.
Right, a 5G GC, representing a good channel, and a 5G DC, a degraded channel.
And they mapped this against a classic kinetic process, a bottle filling station. It's a textbook control loop. A conveyor belt moves a glass bottle. A proximity sensor detects the bottle's edge and fires a signal to the PLC.
The PLC calculates the timing and sends a command to halt the conveyor motor.
A valve actuates, liquid fills the bottle, the valve closes, and the belt resumes. It requires incredibly tight synchronization between the sensor polling rate and the actuator response time.
Under a traditional wired setup, or even a flawless 5G good channel, the system is remarkably resilient to basic network layer attacks. If an attacker manages to launch a volumetric denial of service or injects a machine-in-the-middle payload, say, spoofing a continuous keep-moving command to the motor,
the PLC is polling and transmitting its legitimate stop command so rapidly, often every millisecond, that the legitimate traffic simply overwrites the malicious injection before the physical inertia of the motor can even respond.
Exactly. The network's speed and reliability act as a natural kinetic buffer. The bottle stops exactly under the nozzle, no liquid spills. The determinism of the network mitigates the attack payload.
But introduce the 5G degraded channel, a noisy RF environment. This could be natural multipath fading because a massive metal crane moved across the factory floor, or maybe heavy cell congestion.
And the entire control theory falls apart. The attacker initiates the same DOS flood. The ingress queues of the UPF start to fill up. Now compound that with the degraded radio channel. The modulation encoding scheme drops to compensate for the noise, which drastically reduces bandwidth. The MAC layer starts executing HRRQ retransmissions because packets are failing checksums.
The latency spikes unpredictably, the jitter budget is completely blown. The PLC fires the critical stop command when the sensor detects the bottle.
But that packet gets caught in HRQ retransmission loop. It's delayed by maybe 40 or 50 milliseconds. In human terms, it's a blink. In industrial terms, it's an eternity.
Wow. The conveyor motor doesn't receive the halt command in time. It keeps rolling right past the filling station. The valve logic executes because it assumes the bottle is in position.
And you have a kinetic failure. A catastrophic liquid spill on the factory floor, potentially damaging equipment or causing a safety hazard.
So the attacker didn't need a highly sophisticated Stuxnet-level zero-day exploit targeting the PLC firmware. They simply threw garbage volumetric traffic at a network that was already struggling to maintain RF integrity, and the physics of the factory tore itself apart.
The degraded channel didn't just facilitate the attack, it amplified it into a physical disaster, which forces us to confront how completely broken our traditional defense mechanisms are in this environment. Look at standard intrusion detection systems.
Traditional anomaly detection.
Right. Industrial IDS platforms rely almost exclusively on deep packet inspection and strict time series analysis. In a wired prof and A cell, the PLC sends a polling packet every 10 milliseconds, not 10.5, not 11, exactly 10.00.
So the IDS builds a baseline around that deterministic interval.
Precisely. If it suddenly sees packets arriving at 12 milliseconds, or a spike in inter-arrival jitter, the statistical models immediately flag it as an anomaly. The assumption is that an attacker is manipulating the queues or injecting traffic.
Wait, no, that's not right. If the network is jittery, shouldn't the IDS be more sensitive?
That is the exact vulnerability. The IDS screams constantly. In a 5G architecture, a timing anomaly does not correlate to malicious activity. It correlates to the physics of radio waves. It could be a brief shadow fading event as an AMR drives behind a stamping press.
Oh, I see.
It could be a handover delay as a sensor transitions from one G node D to another. The baseline of normal is no longer a flat line. It's a highly volatile stochastic wave.
And the ambiguity of that wireless medium gives the attacker the ultimate camouflage.
Exactly. They can hide their injected packets or volumetric floods directly inside the natural variance of the radio instability. If you deploy a legacy IDS on a 5G network, you're going to generate thousands of false positives an hour.
The Security Operations Center will experience total alert fatigue. They'll just filter out the alerts or tune the sensitivity so low that the system becomes practically useless. It's a psychological coping mechanism for the SOC analysts, but it's a fatal blind spot for the network architecture.
And if the attackers know they can hide in the RF noise, the logical next step is intentionally manufacturing that noise to create an opening.
Which brings us to the nightmare scenario for wireless ICS, physical layer jamming. We just established that availability is the holy grail of OT, and jamming is a direct kinetic assault on availability.
The reconnaissance phase alone is chilling. An attacker does not need to compromise a firewall or spearfish an operator. They can park a vehicle on a public street adjacent to the factory perimeter with a software-defined radio and just passively monitor the 5G spectrum.
Even if the payload data is heavily encrypted with IPsec or MASEC, the physical radio bursts aren't.
Right, they conduct traffic analysis on the control channels. They monitor the physical downlink control channel, the PDCCH. By observing the scheduling of resource blocks, they can infer the precise mechanical cycle of the factory.
That's terrifying.
They can map the exact microsecond. The bottle hits the sensor, the valve actuates, and the robotic arm swings purely by watching the RF energy spikes.
They map the entire heartbeat of the assembly line from the parking lot. I always picture jamming as a brute force, unsophisticated attack, like some guy with a massive amplifier screaming white noise across the entire 100 megahertz band, drowning out everything.
That is traditional, undirected, wideband jamming. It requires immense power. The Padova research notes it takes around 55 dBm to reliably saturate a cell. That's highly detectable.
Yeah, regulatory bodies like the FCC or local spectrum authorities will triangulate a 55 dBm wideband emitter almost immediately, right?
Within minutes. But the researchers highlight a threat vector that is surgically precise. Narrowband jammers targeting control structures.
Okay, let's get into this, because this is the part that will make you rethink your entire wireless strategy.
5G networks rely on specific, periodic broadcasts to maintain synchronization between the user equipment and the base station. The most critical is the Signal Synchronization Block, or SSB. It contains the primary and secondary sync signals and the broadcast channel. It is the absolute anchor of the cell.
Okay, so if a device cannot decode the SSB, what happens?
It considers the cell lost and drops the connection entirely, forcing a lengthy reattachment procedure.
So the attacker doesn't need to jam the massive data payloads. They just take a scalpel and slice the synchronization heartbeat.
Combined with a directed MIMO antenna array, multiple input, multiple output, they can use beamforming to focus that interference into a highly concentrated spatial beam, aimed through a specific window directly at a critical manufacturing cell.
And this brings us back to the stat from the cold open. A directed MIMO jammer focused specifically on the SSB can force a denial of service pulling just 30 dB meters of power. That is 1 watt. You can power a 30 dB SDR off a standard USB power bank.
If it's in a shoebox.
Exactly. If it's in a shoebox, it can be hidden in a backpack on a visitor, or a drone landed on the roof.
And because the power output is so incredibly low and the beam is so tight, the traditional IT network monitoring tools won't register an anomaly. They won't see malformed packets or volumetric spikes. The targeted machine simply drops off the network.
The operators will assume a sensor failed or a switch died. They will dispatch maintenance, not incident response. So how do you defend against an invisible, low-power sniper that targets the fundamental physics of your connectivity?
You have to push threat detection down to the physical layer using machine learning. The research from the University of Padova specifically tested various AI models to detect these stealthy narrowband SSB jammers by analyzing the radio spectrograms in real time.
Spectrograms, so visualizing the radio waves.
Yes, they benchmarked convolutional neural networks, k-nearest neighbors, and support vector machines.
Why wouldn't they just default to a CNN? Computer vision models are incredibly good at recognizing patterns in 2D data like a spectrogram.
CNNs are highly accurate, but performing deep convolutions on high-dimensional fast Fourier transform arrays requires massive computational overhead. You are talking about millions of multiply accumulate operations.
Which you can't exactly run on a tiny edge switch.
No, in an industrial edge environment, you might have hundreds of radio nodes. You cannot deploy massive GPU clusters to every single edge switch just to run inference on RF noise. The latency and cost are prohibitive.
So they needed a model that was computationally cheap but highly accurate. And the support vector machine won out.
But not just a raw SVM. They combined it with principal component analysis, or PCA, for aggressive dimensionality reduction.
Let's drill into that, because applying PCA to RF interference is fascinating for anyone looking at signal processing. Most background RF noise is highly random thermal noise, random multipath scattering.
But a narrowband jammer transmitting a continuous or periodic signal over the SSB creates a highly correlated structure in the data. So PCA computes the covariance matrix of the spectrogram and extracts the eigenvalues. It strips away all the high-dimensional random noise and isolates the principal components, essentially the core vector of the jamming signal.
It compresses the massive image of the spectrum down to just the mathematical essence of the interference.
Exactly, and passes that reduced feature set to the SVM. The SVM's only job is to find the optimal hyperplane that separates the normal data points from the jammed data points. It is a convex optimization problem that requires very little compute power at inference time.
What does that translate to in terms of detection speed? Because as we discussed with the bottle filler, if it takes a full second to detect the jammer, the liquid is already on the floor.
The PCA SVM pipeline detects the narrowband jammer in 0.11 milliseconds.
A tenth of a millisecond? That is astonishing.
With 95 to 97.6% accuracy, it provides the sub-millisecond physical layer radar required to actually trigger a failsafe or switch the device to a backup frequency before the kinetic process derails.
But spotting the jammer only covers the availability attack vector. What happens if the attacker actually compromises a node? Say they exploit a vulnerability in a legacy PLC that was bridged onto the 5G network, or they spoof the credentials of a temperature sensor.
Right, the lateral movement problem.
Yeah, in a traditional flat industrial network, once you pop one device, you can pivot and scan everything else. How do we prevent lateral movement over the air?
This is where the 3GPP 5G architecture actually provides a massive structural defensive advantage over traditional wired Ethernet or Wi-Fi. It's called network slicing.
The ability to create multiple, logically isolated virtual networks on the exact same physical radio and core infrastructure.
It uses a mechanism called NSSAI, the Network Slice Selection Assistance Information. Usually, enterprises use this macro-level slicing. They'll create one slice with high bandwidth for video cameras, one slice with low latency for the robots, and maybe a best effort slice for employee tablets.
But the research suggests taking that concept to the absolute microscopic extreme, doesn't it? Nanosegmentation.
Yes. Instead of grouping 50 sensors into one slice, you provision a dedicated, mathematically isolated 5G slice for every single piece of user equipment. 1 UE per slice.
That is a logistical paradigm shift for any network architect listening to this. Every single AMR, every individual PLC, every valve controller gets its own personal network.
It is the ultimate realization of a zero-trust architecture enforced at the cellular core. The access and mobility management function, the AMF and the section management function enforce strict isolation for the PDU sessions. If an attacker compromises a temperature sensor, they are trapped in a routing domain of one.
Hold on. If every device is in solitary confinement, how do they interact? The AMRs have to coordinate their paths so they don't crash at intersections.
They don't communicate peer-to-peer at the network layer. The slice only permits routing to the specific backend application, like the Fleet Manager server. The Fleet Manager ingests the telemetry from all the isolated slices, calculates the logic, and sends the individual movement commands back down. The devices never actually see each other on the network.
So even if you have root access on the sensor, you can't ping the robot arm. You can't run an Nmap scan of the subnet because there is literally no subnet. Lateral movement becomes mathematically impossible at the radio and core layers.
Combine that nanosegmentation with rigorous identity management, certificate-based mutual authentication, and MFA for any human access, and you effectively neutralize the blast radius of a compromised edge device.
The concept is brilliant, but deploying and managing tens of thousands of individual slices, managing the cryptographic certificates for every sensor, you can't just wing that. You need a structural framework to ensure you aren't leaving gaping holes in the configuration.
Which is exactly why the transition to industrial 5G leans so heavily on the IEC 62443 standard.
The absolute bedrock of OT cybersecurity. I swear, you walk into any industrial security conference and people are just murmuring 62443 like a mantra.
Because it works. It's a comprehensive series of international standards specifically designed for industrial automation and control systems, IACS. What makes it vital for the 5G transition is that it doesn't just mandate technical features like encryption algorithms, it defines the entire organizational lifecycle, processes, and responsibilities.
The sources are highly specific about how it divides the ecosystem into three principal roles. You have the asset owner, the manufacturing company actually running the plant. You have the product supplier, the vendors manufacturing the 5G base stations, the core software, and the PLCs. And you have the integrator, the engineering firms that stitch the hardware and software together.
And everyone holds a distinct liability. The asset owner cannot just buy a quote-unquote secure 5G router from a supplier, plug it in, and claim compliance. The integrator has to validate the architecture, and the asset owner has to maintain the operational security continuously.
And the standard measures this operational maturity through its 4 maturity levels, right?
Yes. ML1 is initial. It's ad hoc. Processes are undocumented, reactive, and highly dependent on individual heroes in the IT department putting out fires.
Chaos engineering, basically. We've all been there.
Yeah, we have. ML2 is managed. You have documented guidelines, trained personnel, and repeatable processes for things like patch management or incident response. ML3 is defined and practiced. The processes are standardized across the entire global organization, and you have the audit trails to prove it.
And ML4 is improving. You aren't just following a checklist. You are continuously ingesting telemetry, analyzing near misses, and proactively evolving the security posture against emerging threats.
Parallel to the process maturity, IEC 62443 defines technical security levels SLs for the actual resistance of the architecture. SL1 mitigates casual or accidental misuse, an operator typing the wrong IP address.
SL2 targets simple, intentional attacks with low resources, script kiddies running automated exploits.
SL3 scales up to sophisticated means, moderate resources, and specific IACS knowledge. This is where you face dedicated cybercriminal syndicates or ransomware gangs that understand how to manipulate Profinet or Modbus.
And SL4 is the apex. Protection against highly motivated, extensively resourced attackers using sophisticated, prolonged campaigns, nation-state actors, advanced, persistent threats.
The challenge we face today is mapping the legacy concepts of IEC 62443 onto a 5G architecture. The standard relies fundamentally on the concept of zones and conduits.
Right. A zone is a logical grouping of assets that share the same security requirements. All the robotic welders in cell A are in one zone. A conduit is the authorized communication path between zones. In the legacy wired world, a conduit was literally a copper uplink cable plugged into an industrial firewall. You configure an access control list on that physical port, and you have secured the conduit.
But in a 5G deployment, the conduit is probabilistic. It's shared spectrum. The conduit is the air itself. You cannot put a physical firewall rule on a radio wave.
So how do you define a conduit when the transmission medium bleeds through the walls?
You have to abstract the conduit away from the physical layer and tie it to cryptographic identity. The conduit now encompasses the physical radio coverage, yes. But more importantly, it includes the device identity management, the life cycle of the subscriber credentials, and the edge computing routing rules. Securing the conduit means securing the fundamental root of trust of the device attempting to access the spectrum.
Which brings us to the convergence of telecom authentication and industrial authentication. 5G inherently has robust security protocols like 5G aka authentication and key agreement, or EAP aka. They use a challenge response mechanism with sequence numbers to prevent replay attacks, validating the device against the authentication server function in the core.
But those protocols traditionally only authenticate the telecom hardware to the telecom network. They don't authenticate the industrial application to the industrial controller. The massive push right now is bridging those domains using hardware roots of trust, specifically the UICC.
The Universal Integrated Circuit Card. The tamper-resistant physical SIM, or eSIM, inside the industrial modem.
The industry is developing a generic Trust Anchor API. This allows the industrial application layer, say, an OPC UA pub-sub client running on a robot, to access the secure enclave of the telecom UICC. The industrial protocol can use the telecom SIM's cryptographic capabilities to sign its own payloads or establish TLS sessions.
Okay, I need to visualize this. Let's use an analogy. Think of the legacy wired network like an exclusive nightclub.
We're really going with a nightclub.
Stick with me, it works. In the legacy wired architecture, perimeter security was like having a massive intimidating bouncer at the front door. He checks IDs at the perimeter, but once you are inside the club, it's a trusted zone. You can wander over to the bar, you can walk into the VIP section, you can talk to anyone.
The classic M&M model. Hard, crunchy exterior, soft, vulnerable interior.
Yeah.
Once an attacker breaches the perimeter firewall, they have free rein to pivot.
Exactly. But with 5G nanosegmentation and the generic Trust Anchor API tying the industrial payload to the hardware SIM, we aren't just relying on the bouncer at the front door. We are upgrading to assigning a personal, highly trained, heavily armed bodyguard to every single VIP inside the club.
The bodyguard represents the secure enclave of the UICC executing the cryptography.
Right. The bodyguard checks your 5G aka credentials before you can even step onto the dance floor. And because of nanosegmentation, if you want to talk to another VIP across the room, you can't just walk over. Your bodyguard has to cryptographically negotiate with their bodyguard via the central security broker before a single word is exchanged.
It is the absolute enforcement of zero trust at the hardware layer, mapped directly to a radio layer. And it is mandatory because the club is no longer a concrete building with a single door. The club is wherever the RF signal propagates.
It's brilliant in theory, but theory doesn't manufacture automotive chassis or fill bottles. A blueprint is just a PDF until someone actually writes the code, builds the hardware, and drops it onto a loud, vibrating, dirty factory floor.
And this is where we see the theoretical frameworks of 62443 manifesting in actual deployable enterprise architectures. The vendors recognize that IT and OT can no longer operate in silos.
The sources highlight the collaboration unveiled at Mobile World Congress between Siemens and Palo Alto Networks. This is the collision of a massive industrial automation legacy with top-tier IT cybersecurity. How are they actually integrating this?
They are merging Siemens' private 5G infrastructure, the distributed unit, central unit, and 5G core, with Palo Alto's AI-optimized next-generation firewalls.
But you can't just take a standard IT Palo Alto appliance, drop it in line between a PLC and a high-speed robotic arm, and turn on deep packet inspection. The firewall would induce so much processing latency that the control loop would instantly desync.
That is the core engineering challenge. The NGFW has to be optimized for the specific deterministic traffic patterns of industrial protocols. But the crucial innovation in their architecture is how they deploy the CNET security monitor.
Synex. How does it inspect the traffic without breaking the jitter budget?
By operating entirely out of band, it utilizes passive, non-intrusive anomaly detection. Instead of sitting in line on the user plane function and acting as a physical bottleneck, the UPF mirrors the industrial traffic via a span port or tap to the Synex monitor.
So it's just a copy of the traffic.
Exactly. Synex performs the deep packet inspection on the mirrored payload. It maps the assets, identifies unauthorized protocol usage, and scans for malware signatures asynchronously. It provides complete visibility into the industrial application layer without ever inserting a single microsecond of delay into the live ProfNet control loop.
So going back to the analogy, the Cynic monitor is the eye-in-the-sky camera system watching the bodyguards in the club. It observes everything, detects suspicious behavior, and alerts security, but it never stops the patrons to frisk them while they are dancing.
Because in manufacturing, if you stop the dance, you bleed revenue. Which brings us to the most profound realization of this entire architectural shift. In traditional enterprise IT, cybersecurity is heavily biased toward confidentiality. The primary objective is preventing data exfiltration. Don't let the threat actors steal the customer database or the intellectual property.
But on the OT side,
On the OT side, a momentary disruption does not have to result in kinetic damage to be considered a catastrophic success for the attacker. If a 30 dBm narrowband jammer forces a robotics cell to drop its connection for 2 seconds, or a malformed packet triggers a safety interlock that halts a conveyor.
the material flow stops, the sequencing of the entire plant desyncs, the batch of pharmaceuticals is ruined because it sat outside the temperature parameters for too long. The attacker doesn't need to encrypt a single hard drive with ransomware, they just need to introduce enough latency to break the physical timing.
In the industrial 5G era, cybersecurity becomes completely indistinguishable from operational uptime. If the network stutters, the factory dies. Security is uptime.
It's the darkest irony of Industry 4.0. We spent decades designing these incredible, autonomous, self-optimizing digital twins to make manufacturing effortless, to make our Fridays easier. And instead, we've engineered a reality where we spend our Fridays sweating over invisible radio waves, sub-millisecond HRQ retransmissions, and physical layer jamming from a shoebox in the parking lot.
We successfully traded the physical constraints of copper cabling for the mathematical anxiety of probabilistic spectrum.
You really did. But for everyone listening right now, whether you are architecting a greenfield 5G deployment, managing a legacy plant, or just trying to keep your digital twins breathing, here is the reality check.
The foundational question is not whether industrial 5G works flawlessly on a clear day. The throughput and agility are spectacular when the channel is clean.
The real question is how your kinetic machinery behaves when the radio layer inevitably degrades. Do you have defined deterministic fallback modes? When the air itself becomes hostile, either through natural interference or a directed 30 dBm attack, what is the recovery logic?
You can no longer treat the network as a transparent utility. The private 5G core is critical OT infrastructure. You have to design the physical safety interlocks, assuming the wireless signal will eventually fail.
Check your systems. Check your assumptions. And maybe, just maybe, question whether what you trusted yesterday is still trustable today.
That's all for this episode of Cybersecurity Under Pressure. Real attacks, real lessons.
See you in the next chapter.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared, stay critical, and keep following the evidence.